Welcome everyone. Today is March 30th, and this is another of our biweekly dashboard group calls. My name is Mati, and I'll be your host today. We have agenda packed with topics, so let's get right into it. Let me quickly make Albin co-host so that he can share, and I'll just stop sharing the screen.
Thank you.
Take it
Let me
away.
see if Thanks. Can you just give me a thumbs up so you can see my screen, please?
Yep, we can see your presentation.
Excellent, perfect. So let's get into it. So my name is Albin Severinsson. I work for G Research in London, and I'm one of the developers working on Armada, which is a batch scheduler for Kubernetes. And in particular, today I'm going to be talking about the scheduling components, so the component of Armada that assigns pods to nodes that we developed specifically for Armada. And so, as mentioned, I'm at G Research, which apparently, according to the website, is Europe's leading quantitative fairness research firm. We have offices in London and Dallas. And of importance to this presentation is that we run millions of batch jobs per day for data analytics purposes in order to develop algorithms that can predict how the markets move. And so the mission then of G Research is to build the world's leading finance research platform using, in our case, almost exclusively on-premises compute. And as part of sort of the development of this mission, it's been decided that more compute is more good. And so we need some solution that can manage a lot of compute for running all of these batch jobs. And specifically, the scale we have in mind is on the order of 1 million cores, being able to schedule on the order of thousands of jobs per second, and to ingest into the system hundreds of thousands of jobs per second. And in addition to those, we want all of the sort of nice scheduling features that people are talking about, such as resource fairness and limits, preemption, gang scheduling, and excellent observability. Furthermore, at G Research, we want to have essentially a shared pool of compute that we use for everything, right? So we want to have shared resources for running, services, perhaps workstations, and batch jobs. And this has led to us using Kubernetes for basically everything that we do. However, scaling Kubernetes beyond some limits, say 1,000 nodes, is quite challenging. People have done it, but you have to jump through some hoops. And in addition to that, Kubernetes doesn't like large bursts. So as I'm sure all of you are aware, Kubernetes is backed by etcd, and etcd has great consistency and durability guarantees, but is relatively slow in handling large bursts of load. And in fact, you can kill your Kubernetes cluster if you submit too many pods. And so the solution we've arrived at then is to have some higher level system that multiplexes across many different Kubernetes so-called worker clusters. And this comes with some nice benefits, in particular that you get better throughput and reliability compared to having a single cluster. You lose a cluster, you don't lose all of your resources. And you have the throughput equal to the product of the number of clusters you have and the cluster capacity or throughput. It also has operational advantages in that you can update one cluster at a time or before you roll it out to all of your estates. Also comes with some drawbacks, naturally. Using an approach like this, you have no direct access to the underlying worker clusters. Right, everything has to go through the high-level system, and the high-level system has to either transparently pass things through or understand what you're trying to do and translate that into something that the worker cluster can understand. And obviously, this is the idea, right, in computer science, that all problems can be solved by adding more layers of abstraction, except for the problem of having too many layers of abstraction. And clearly, Armada is another, or this high-level system, which will turn out to be Armada, is another layer of abstraction. And so G Research, this is at the high level, the architecture that we arrived at. They are quants or researchers. They express their workloads typically in the form of a directed acyclic graph, where each node in the graph is a task. So that as tasks complete, other tasks can start. They express these tags in some form of tooling, And that tooling then knows how to convert those directed acyclic graphs into pods that are submitted to Armada. Armada is then able to schedule those pods across many different Kubernetes worker clusters. And when it comes to the Armada scheduler, we've been sort of on a journey for the last, say, 1 year, where initially Armada would just handle queuing. So you'd submit your pods to Armada, Armada would store them inside its sort of specific queuing data structures and would sort of drip feed those into the Kubernetes worker clusters, where Kube Scheduler would take care of all scheduling. So Armada basically had no scheduling component of its own. The second step was that we added to Armada some scheduling functionality that allowed Armada to, with fairly high accuracy, predict what the Kube scheduler would do, so that you could avoid giving pods to a worker cluster unless you were fairly confident that that cluster could actually schedule that pod. And we had a feedback loop such that any pods that could not be scheduled, because there's a correlation thing here, right, were fed back to Armada and retried on another cluster. And finally, and this is quite recent as of the spring, and this is what we do currently, is that Armada now does all scheduling. So effectively, we are bypassing Kube Scheduler at this point, where Armada assigns pods to nodes. And the way we specifically do this is we have in Armada, we add a node selector onto each pod that specifically targets a single node. You can think of the kubernetes.io/hostname label, for example. Later on, we may even set the node name directly on the pod. And there's a couple of reasons why we've done it this way. And I'll go into these reasons, and I'll explain sort of how the solution that we've developed, the scheduler we've developed for Armada, differs from Kube Scheduler. And sort of at the high level, the reason for sort of why we want to have another scheduler is that Kubernetes is designed to evolve to a desired state, and that desired state is assumed to be feasible. And if you have infinite compute resources, right, that's always fine. So you can always schedule, like you can always put pods into the system and expect those to eventually be scheduled if you have an infinite amount of resources. And as we all know, the cloud is infinite. So if you are operating in the cloud, like this may be fine for you. You can just have all of your users submit their pods to Kubernetes, and the cluster autoscaler will automatically expand the size of your cluster until you get the resources you need. But sometimes, clearly, you don't have an infinite amount of resources. Indeed, the cloud is not even always infinite. One such example is whether you're requesting resources that are contended for by other people, like high-end GPUs. Alternatively, if you have a finite amount of money, there's a finite amount of compute that you can buy from the cloud providers. Right? And in these cases, when you don't have an infinite amount of resources, so the desired state of the system, so the state corresponding to having all of your pods being scheduled, may indeed be infeasible. And what you need to do instead is you need to find some good feasible state, because the desired state is infeasible. There's a trade-off between different things that you want. And there's a couple of different strategies that you can use to achieve that. So first, you can use financial costs and incentives. This is what the cloud providers do, right? They charge you for the amount of compute that you use. And if you want more compute, you pay more money. And at some point, there is sort of diminishing returns, presumably, in the value you get from the compute that you assign to the clusters. And at some point, you just decide to stop paying. Within an organization, this might be implemented by having each department sort of basically pay for their own compute. But fundamentally, this means that every actor that submits any sort of workload has to be aware of the cost and value of the work that they're submitting, because they have to make a call whether the additional cost of submitting this workload is worth the benefit. So other approaches include resource limits, which may be hierarchical, such that you limit the amount of resources that you have, that each user can be given, right? And this is also a popular approach in organizations, and it's a way in which you can limit the amount of compute and hence money requested for by a single department or team or a person. And finally, there's the approach of fairly dividing some fixed size pool of resources. So if you're on premises, clearly you have to use approach 3. You have no choice, right? But even in other approaches, if you're using an infinite cloud, you may still have an interest in 3 if you have, say, a total budget for your organization that determines the amount of compute that you can buy at any one point in time from a cloud provider. At that point, even though you're buying resources from an infinite cloud, the amount of resources that you can buy is finite and has to be shared in some way between the users of that capacity. And Armada is designed to find some good state under resource scarcity using approaches 2 and 3 of these strategies. And specifically, Armada introduced these features in terms of scheduling. First, there's a separation of cluster scaling from scheduling. Right, so as mentioned before, you may have a certain amount of compute that you want to buy, and you want to determine separately from scheduling how much compute you want to buy at any one given time, and then schedule across the compute that you have available once you bought it. Or if you're on-prem, obviously it's limited. Resource limits, so you can determine one, sort of how much capacity or resources any one user can be given, and at what rate they can be given those resources. Armada also introduces fair scheduling and preemption, meaning that when we schedule pods, the order in which we schedule those pods is determined by the resources already assigned to the people that submitted those pods. Similarly for preemption, when we preempt pods, we start by preempting people that have more resources relative to people that have less resources. Right, so it's a fairness-aware form of preemption. And this is based on queues. So Armada has an internal notion of a queue, and each pod is associated with a specific queue. Armada also introduces inter-priority class preemption. Right, so in Kubernetes, a higher priority class can always preempt a lower priority class. But in Kubernetes, pods of the same priority class cannot preempt each other. However, in Armada, we have this feature, and I'll go into some more detail on this next. Armada also has gang scheduling and gang preemption, such that a set of pods can be scheduled in a way, in an all or nothing manner, such that if any one of them can be scheduled, they're all guaranteed to be schedulable. And similarly, if any one of them is preempted, all of the pods in that gang are preempted. And finally, Armada introduces lots and lots of knobs that you can use to control all of these processes. You can have a look at the right of the slide, where on the top, we show GPU allocated per user. So each color then corresponds to a different user. And the red line at the top is the total capacity of the cluster. As you can see, this is a very typical scenario for one of our worker clusters, where you have many users and they share the available finite amount of compute. And on the bottommost graph, we show the GPU demand. So as you can see, there's a red line in the middle, which is the total capacity, the number of GPUs available. And then there is matched and used, which is the currently assigned GPUs, so GPUs that are assigned to a pod. And as you can see as well, that the number of queue GPUs is about a factor 2 of the total available. Right, so this is very typical for our how we use Kubernetes and batch, in that we have often way more capacity in the queue than what is currently allocated. Right? And this goes back to what I've been saying previously, which is that you need some way of taking a fixed amount of compute and dividing that, finding a feasible state that you like. I also want to go into some detail on preemption specifically. So when you preempt for services, the typical scenario, right, is that all of your services at any one point in time can fit on your cluster. For batch, things are a bit different because you have this long queue. And for batch, in my opinion, there are two reasons for which you would like to have preemption. The first is what I call urgency-based preemption. And this works in exactly the same way as Kubernetes priority class-based preemption, where a pod or a job of higher priority class can preempt a lower one. Right? This can be interpreted as the higher pod, a higher priority class pod, it being more urgent. It should be run before some other currently running pod, and the currently running pod has to be kicked off to make room for the higher urgency pod. Right? And the reason why we have this is that clearly for batch, all pods have a finite lifetime, right? If you just wait long enough, all of your pods will eventually run. And preemption then only affects the order in which you run them, right? Which is why you should interpret this form of priority class preemption as urgency-based. The second reason for why you may want to have preemption is for fair share reasons. Say you have a cluster with some amount of capacity and you have a single user, you may want to give, so if that single user is the only active user on the cluster, you may want to give all available capacity to that one user, right? But at this point, unless you're careful, that user may have effectively kidnapped all capacity in your system. If a second user comes along, you may have nothing left to give to that user. And this is the second reason for why you may want preemption. You may want to preempt jobs assigned to, say, column user A in order to give those resources to user B, who came along later. And preemption also has sort of advantages in that allows you to more easily schedule large jobs. You can move things around, preempt and restart things to make room for a larger distributed job. It also allows you to get small amount of resources quickly. And the way we operate Armada at Research is we have two priority classes. We call them Armada Default and Armada Preemptible. Armada Default can always preempt Armada Preemptible. Armada Default cannot preempt other Armada Default jobs, but Armada Preemptible jobs can preempt other Armada Preemptible jobs, or pods, as we express our jobs. And you can see this in action here. So here I have a scenario which is exactly the one I described previously. We have a user A, which is the green curve in the graph. We give all capacity to user A. Later on, user B comes along, the yellow color in the graph, and we preempt some of the jobs of user A to give to user B. And here, the weights of the queues, so each queue in Armada has a weight associated with it, are such that the fair share of the green curve is 2/3 and that of the yellow is 1/3. So you can see how this is process whereby the green curve is preempted down to the new fair share, right? Before user B comes along, the fair share of QA is 100%. But after user B comes along, the fair share shifts because now there are more users who want to share a fixed amount of capacity, such that the fair share of user A becomes 2/3 and that of user B 1/3. So as a sort of final thing I want to talk a bit about. So previously we talked about sort of what we want to do and what the features are. Next, I'll talk briefly about how we have implemented this for our scheduler. And it's a bit different compared to the approach taken by KubeScheduler. So essentially what our scheduler does is it looks at the current state of the system, where the current state of the system is captured by a mapping from jobs to nodes. Right, so any job that is currently mapped to a node is currently scheduled, right, assigned, and any job that has no mapping to a node is queued. So the scheduler looks at the current state of the system, and given that current state, computes what the ideal state of the system is. And in doing so, it accounts for the urgency of jobs, fairness between different users of the systems, resource limits, and the cost of preempting running jobs. If you're sort of interested in this approach, I can recommend a paper. It's a couple of years old, but it's quite interesting, which is called Quincy. And so in a bit more detail, how this works, this is how one of the scheduling cycles of Armada looks like, where at the start of each scheduling cycle, Armada looks at the jobs currently in the system and does what you call an eviction, meaning that it does sort of a fake scheduler internal preemption, where it takes pods currently assigned to nodes and puts them back at the front of their respective queues. Then it performs a scheduling round as if those evicted jobs have never been scheduled and were still in the queue. At this point, the scheduler then computes a new mapping from jobs to nodes. Finally, Armada reconciles against this new computed mapping. And so any job that was evicted in step 1 or in a pod and then not rescheduled in step 2 is preempted. Any job that was scheduled in step 2 but not previously evicted is a new job that should be scheduled. And then urgency-based preemption consists entirely of scheduling more urgent jobs first. So scheduling first jobs of higher priority classes. Preemption the fair share, on the other hand, is implemented via the order in which we select which pod to schedule next. And the way we do that is based on the current assigned resources of each queue. So when we schedule, we select first which queue to schedule from, and then we select within that queue the next job or the next pod to schedule. And the way we select the next queue to consider is we look at all the queues, we compute what fraction of their fair share each queue has been assigned, and we select the queue which currently has the smallest fraction of its fair share. You can view this as a sort of water filling approach. If you look at the diagram in the top right, this is basically how it looks, where you have some previous resource allocation, and then you build up the resource allocation of each user gradually, each queue, such that they are made as even as possible, such that each user is given as close as we can get to its fair share as we can. And that's essentially it. So these are the features that Armada introduces and how we did them. So it's a fairly high level overview, I think. And I think that sort of the things that would be useful to add to Kubescheduler for batch are the things that I specifically mentioned that Armada introduces on one of the previous slides. But I think I'll stop here and I'll take questions, and then we can go back to any more slides in case people have questions about that. Yeah, so Marcin?
You mentioned like 2 or 3 slides ago that the green traffic will get 2/3 and yellow will get 1/3. Why 2/3, not 50-50?
Right. So in Armada, we have this notion of a queue in Armada, and each queue has associated with a weight, and those weights determine the relative fair share of these queues. So in this instance, the weight of the green curve is 2, and the weight of the yellow one is 1, which means then that the total sum of the weights is 2 + 1, 3.
Oh, okay.
And yeah, exactly. So that's how it works. So if the weights of each queue had been equal, then it would have been 50-50, as you suggest.
Okay.
There's a question on the chat regarding resource limits. Is there any notion of max load time in Armada for scheduled tasks? How do you handle calling a long-running task? Hold on, let's see. That have gone rogue and are not doing any real work. Even with preemption, presumably there is some amount of running pods that a user has running with default priority that is not preemptible. And with preemption, do you have a mechanism for checkpoint restart for any running jobs? What is the default time window for shutting down preempted pods? Is there an interrupt signal to jobs that it knows to save any necessary data?
Yeah, so sure, let me go into that. So first of all, in Armada, we have default active deadline seconds, right? So each Kubernetes pod can have a active deadline in seconds, which is a number of seconds after which the pod gets killed. And so we have default values for all pods, and users are required when they submit jobs to put a finite number of seconds for that, right? So clearly they could put 10 years, but usually people don't, and this is one mechanism by which we avoid having jobs last forever. We also have tooling that does what we called stuck job detection, where they're basically watchdog timers that look at the output generated by jobs. And if there's no output generated in some amount of time, that job is assumed to be dead and is killed by the tooling. Let's see. And similarly for checkpointing, again, we use various ML frameworks and tooling that has built-in mechanisms for checkpointing. And we do allow people to set the graceful termination period on pods, which allows people to have some amount of time to shut down once they've been preempted. So how it works is that if you set a non-zero amount of graceful termination period, you get first a sig int, then you have up to that time you specified, which you limit to be 5 minutes or less, to shut down, after which you are given a sig kill if you haven't already shut down. Hopefully that answers your question. Which one? Who is the next one?
Abdullah was first.
Go for it.
For gang scheduled jobs, how does preemption interact with these jobs? Like, do you preempt the whole job or do you preempt it partially? That's one. The other thing, do you have a notion of, like, for a gang scheduled job, I'm assuming it's multiple pods, right? Like, and if one pod fails, and do you restart that pod or restart the whole job? Do you do that by restarting the other pods in place and recreating the failed pod, or recreate the whole thing?
So for the preemption, what we do now is we have sort of gang atomic preemption, such that when we consider jobs for preemption, we consider them for preemption on sort of a gang level, meaning we either preempt the whole gang or none of them at any one point. Mm-hmm. And there is some edge cases here regarding sort of jobs finishing. So it could be right that you start out with 10 pods in your gang, 2 of them succeed and are no longer running, and you have 8 remaining. At that point, the system understands that the sort of correct number of running pods is 8, and it knows to preempt 8 pods or no pods when it makes a preemption decision. Let's see, what was the other question?
When a pod fails.
Right.
What do you do? Like, do you restart the whole gang or recreate it?
So again, we have tooling for doing this, where the pods that make up a gang are aware of each other.
Okay.
And if one of them goes away, they all bail out on their own. And we have tooling that sort of recaptures that gang, resubmits it to Armada, and have it be rescheduled atomically. That may change in the future, but for now, this is the case. Who's next?
Okay.
Okay. I think Michal was next.
So I have a question. How do you model the jobs? Is it like, is the job like the Kubernetes job, or other types of job CRDs are supported as well?
So
on your own job concept.
We do have our own job concept, but it's very tightly related to to Kubernetes pods. So an Armada job is essentially a Kubernetes pod with a couple of extra fields, such as the name of the queue and also the priority of that job within the queue. We also add something we call a job set, which is essentially like an annotation on the job, which allows you to manage them as a unit for things like reprioritization and cancellation. People typically submit, tens and tens of thousands of jobs, and having job sets then allows you to atomically, or sort of as a unit, change the priority of all of those jobs or cancel them. Hopefully in the future, I would like us to be able to have it such that you can submit some form of vanilla Kubernetes object directly to Armada, and Armada be aware of that and be able to schedule that sort of transparently for you, such that you can do basically either kubectl apply-f or Armada submit, and you would use the same object for those. But there's perhaps a couple of things missing before we can do that. In particular, queue is very important to us. Does that answer your question?
Yes, that's exactly what I wanted. Okay.
Okay, Martin, you're up next.
Okay, so on one of your first slides, you mentioned quite impressive numbers regarding like the throughputs that your system have. like tens of thousands of jobs and per second and so on. So what is your scheduling infrastructure? So how fast you can do it? Do you do all of the computations that regular scheduler does for all of these millions of cores across your clusters? Could you please shed more light on how it is organized?
Yeah, sure. So first of all, the Armada scheduler does understand all of the Kubernetes scheduling concepts, such as, taints and tolerations and node selectors and node affinities. But we have various optimizations put into the scheduler that allows the scheduler to very efficiently handle sort of common scheduling requirements. In particular, we have nodes stored in an in-memory database with various indexes that allow Armada to quickly remove from consideration lots and lots of nodes that could not be scheduled onto. And this is the way in which we are able to sort of make the scheduler very, very fast. I believe the numbers that we have today are on the order of, 4 million jobs a day, something like that. So from that, you can compute the sort of average scheduling time that we have. And we do have capacity for scheduling, I believe, thousands of jobs per second. In addition, we have, due to the architecture of Armada, submitting a new job to Armada only consists of having a message put onto a message bus for which we use Pulsar. And so submitting new jobs into the system is an operation that can handle very, very large bursts. And so submitting hundreds of thousands of jobs to Armada only takes a couple of seconds. And then asynchronously in the background, those are ingested into the scheduler logic. And the scheduler logic can then sort of keep those things in memory and perform very, very quick scheduling decisions. We're also looking into other optimizations, in particular involving how you manage many pods that have the same scheduling requirements. Because something that often happens, right, is we'll have a researcher, he'll have, 10, 20,000 jobs, whatever, but they're all the same. They're all like maybe 1 GPU jobs. And once you can't schedule it, one of those, right, you can just immediately give up on all of the other ones and start considering jobs that have different scheduling requirements. That's an optimization that we're very likely to add sometime soon.
Cool. One more question, if I may. What about traffic from not scheduling pods, but starting the pods on the node? So we still need to get to etcd and we'll put some quite big load on the masters. Is it a problem, or you also optimize it somehow for like huge bursts?
So that is a problem. And we limit the rate at which we schedule stuff in order to not kill our worker clusters. In addition, we have a component that continually monitors the health of etcd and backs off on creating new pods when etcd is looking a bit weak. And finally, we create naked pods always. We don't create any deployments. We don't create any jobs or stateful sets or anything like that, because all of that creates additional load onto etcd. So it's always just naked pods. And actually something that will help us a lot is having sort of batch operations for the Kube API. Like that's something that would be very, very beneficial, because then we could speed things up considerably. We anyway schedule large numbers of pods at any one given time, right? So,
cool. Thank you.
Aldo, you're up next.
We're running out of time, but I guess I would have liked to see more of the last thing you said, like putting down some of these things into Kubescheduler. Like, can you be more specific about which things you think could be pushed upstream? Because currently Kubescheduler doesn't have a concept of queues, and even if it did, I feel like since Armada is multi-cluster, I don't know how, like, if you're already managing quotas at the multi-cluster level, does it make sense for a scheduler to also do it at the cluster level?
So I do think that if you want to have multiple clusters, clearly whatever queuing notion you have has to be at the step above the clusters, right? Because the queues have to be across clusters. I still think probably there is a use case for people that want to have queuing within a single cluster. Right, indeed, Armada does bring some benefits also for people who have no interest whatsoever in multi-cluster.
I guess my question there would be, do you see a world where there is the kubescaler queuing system running in addition to the Armada queuing system running? Because well, now you're re-implementing kubescaler. So I'm failing to see how they could work together. So I guess as a piece of feedback on the presentation, I would have like presentation to focus more on that. So we can actually discuss some possible things we can do in scheduler.
Yeah, so that depends entirely, I think, on whether people want. So I sort of presented this as the things that we found lacking in Kubescheduler and we chose to re-implement ourselves because they're not available in Kubescheduler. My assumption would be that other people have similar needs to us, but they may not have the multi-cluster need, in which case, if these things are available in vanilla Kubernetes, right, they will not need Armada. Indeed, my original view that I had sort of months ago on the interaction between Armada and Kubescheduler was that Armada would make a very lightweight scheduling decision, give pods to the Kubescheduler. Kubescheduler in each cluster would make sort of local decisions, sort of a divide and conquer manner. And then there will be feedback from Kubescheduler to Armada, and Armada would sort of be compensating for things that didn't happen in the way that was expected. And so if Kubescheduler understood things like queues and fairness and preemption according to fairness, right, we could just continually feed from Armada pods into Kubescheduler, into the worker clusters, and then have feedback to sort of continually tune how we do that. But because these things are not available, we have to re-implement everything ourselves, right? For all of these fairness and preemption things. Right, and then
I would like us to follow on this idea of feedback loops. I think that's something useful, but I'm just concerned that now that you have completely formed scheduler, those discussions will stall. I hope that's not the case, but I hope we can get back to a design where the scheduler still takes these local decisions that you mentioned. But yeah, we need changes in scheduler for sure, but we need those discussions to happen so we can make progress.
Yeah, I'm happy to partake. I mean, in any case, right, these are the things that we needed but didn't have in Kubescheduler, and that would be needed to add to Kubescheduler for us to be able to have this feedback approach.
Yeah, and also for everybody else here, like, well, we are making a lot of these implementations outside of scheduler for single cluster in queue, which has a lot of these concepts that you mentioned here for single cluster. So ideally, there will be these three components working together, but sounds very far away in the future at the moment.
Yeah, I agree. That would also be something I think quite nice. Although again, that does put more load on etcd, which is something that we are a bit concerned about.
Okay, in the interest of time, Abdullah and Martin, can I push your topics over to the next time?
Mine is quick ask, if I may. I shared the job set document that I presented a month ago on all. And my ask here is, I would like to, we started like a rough implementation in a private repo, but we would like to ask the community to have a sub-project sponsored maybe by SIG apps or SIG scheduling to continue iterating over this with the community. I don't know, Magic, if you can, is this a proper place to discuss this and maybe approve this, or do you want to open? Should I open an issue and then tag? I don't know, like, is the working group here enough to have enough power, like, to actually sponsor this project, basically?
I mean, we sponsored the queue, if I remember correctly.
Yeah.
So I would probably see this in a similar vein and use that as well to develop whatever we want, and then at some point in time, eventually we can make eventual decision whether we want to push this into the core or it will be left as a SIG maintained eventually project. But yeah, I think that that's a reasonable approach.
Okay.
I've noticed that you advertise this topic in both the batch SIG apps and SIG scheduling. Yeah, just double checking group. So I think that should be sufficient.
Okay, so I will then create an issue and tag you on it as SIG app representative, and hopefully we can start the repo.
Okay. Martin, can we push the Spark on
Yeah, just it will be like a 30-second announcement, if I may. Okay, so if you are using Spark on Kubernetes operator from Google Cloud Platform and you would like to be more involved in its development, please let me know. We are trying to put more life into the project and move it to some more open environment than Google's own repository. Please ping me on Slack, on an email, or ask on the next meeting, whatever works for you. Okay, that's all. Thank you.
Awesome. We're a couple minutes over. Thank you very much all for today, and see you next time. Bye all.
Thank you.
Thanks everyone.
Thank you. Bye.